So welcome everybody, and first and foremost, Happy New Year. And welcome to the new season of our webinar series on data science and statistics. As many of you may know, this is an initiative from a group at the Faculty of Economics of the University of Porto, and which was launched as other similar initiatives during the lockdowns in an attempt to keep the community together. And the first seasons, let's say, only featured Portuguese researchers in statistics, machine learning, data science, in an effort to keep the Portuguese community working in these areas together. But now we can all fortunately meet again. And after a short break for reorganizing, we thought it was high time to open up and internationalize this initiative. And this is the first session of the new season of DaSSWeb. And to start this season, David Hand has given us the honor to be the first speaker. Of course, David is someone who does not need a presentation, but let me summarize his current position. David Hand is now Emeritus Professor of Mathematics and Senior Research at Imperial College, where he previously held the chair of statistics. As everybody knows, he has wide research interests ranging from the foundations of statistics and measurement, challenges of data mining, big data, and artificial intelligence, to also modern cutting-edge data science tools. He is author of several books, including The Improbability Principle, Dark Data, From GDP to Sustainable Well-being, Principles of Data Mining, and most recently, Amy's Luck. David, thank you so much for having accepted our invitation. It's really a great honor for us to having you in our series. And we are eager to hear your talk, which today is on dark data and why what you don't know matters. Thank you very much. And the floor is yours.
Great. Thank you very much indeed. The honor is mine. Thank you very much for inviting me. I'm going to kick off by attempting to share my screen. And right, you should now be able to see my title slide. Can you can see the title slide?
Yes, that's fine.
Great.
Yes.
Okay, perfect. Thank you very much. So as I said, thanks very much for inviting me. This talk is based on my recent book with the same title, Dark Data, Why What You Don't Know Matters. And I should say at the start that this book is, it's not a technical book. It's a sort of a book for lay people, non-expert statisticians, because I think it's so important that the community in general understands this. What that means is that neither the book nor this talk has equations in it, but it does talk about data and the implications, but it doesn't have any technical maths in it. So obviously a good place for me to start is by telling you what I mean by dark data, and that's what I'm going to do. But I'm not going to give you a definition. What I'm going to do is open with 4 examples which illustrate the sort of thing I mean. So here's my first opening example. This is an anecdote which many of you will be familiar with, but it illustrates the ideas nicely. You're walking down a road and you come across an elderly man putting little piles of powder down the center of the road. And you say, "What are you doing?" And he says, "It's elephant powder. It's to keep the elephants away." And you say, "But there are no elephants here." And he says, "Yes, it's wonderfully effective, isn't it?" Of course, what he's missing is what would happen if he didn't put the elephant powder down. If he didn't put the elephant powder down, he might discover that that was just as effective as at keeping the elephants away. In fact, he might then go on to discover that there were no elephants to be kept away. So he's missing something crucial. He's missing information, data about what would happen if he didn't put the powder down. Crucial dark data. A silly little example. Here's one which has exactly the same mathematical structure as the elephant powder example, but much more serious implications. Around the year 1985, about 1.2 million people around the world died of measles. Then, thanks to the miracle of modern medical science, namely vaccination, that has now shrunk to about 100,000 nowadays. Actually, that's not quite true. It was around 100,000 in 2018, but it's doubled in the last 2 or 3 years for various reasons. But due to the modern medical miracle of vaccination, the number has been reduced dramatically from 1.2 million. In fact, since the turn of the century, about 25 million lives have been saved because of measles vaccination. Actually, that's not quite true either. It's recently been discovered that measles damages the immune system, and it's thought that about 4 times as many people die of other diseases because of their damaged immune system from measles as die of measles itself. So we're really talking about 125 million lives saved since the turn of the century. And this damaging the immune system obviously is reminiscent of COVID and long COVID. In the position of a parent of a young child, 100,000 a year isn't very many around the world, not very many. So this parent might say, well, look, nobody I know has died of measles. None of my family, friends, workmates, none of my child's schoolmates have died of measles. I think the danger is exaggerated. And on that basis, they might decide not to. Again, like the elephant powder example, what they're missing is crucial information, data on what would happen if they didn't vaccinate. I just got my connection is unstable. If my connection should stop or whatever, please try to let me know and I'll do something. Anyway, the point about this is that they're missing crucial information, just like the elephant powder example, but with much more serious implications. My third example is a classic. In fact, it's such a classic that I decided not to include it in the book, and many of you will be familiar with this. During the Second World War, Allied aircraft returning from sorties over Europe came back peppered with bullet holes, like in this picture. And the question rose, where should you put armor on these aircraft to protect them? You can't put the armor everywhere, or things would never get off the ground. The obvious answer is, well, you look at the aircraft, see where all the bullet holes are, and put the armor there. But a very clever man named Abraham Wald, working at the Statistics Research Group in Manhattan at the time, said, no, that's quite wrong. You should put the armor where the bullet holes aren't. His reasoning was that aircraft like this, with lots of bullet holes in particular places, came back safely. The ones you didn't see were where you should put the armor, because clearly they'd been shot down. And those would be the ones where there aren't any, where the bullets entered the engine compartment or the pilot compartment. So again, crucial missing data, the aircraft which didn't come back. And then my final little introductory example is Hurricane Sandy. October 2012, at the time, the second most costly hurricane in American history. It caused $75 billion worth of damage and killed 200 people. But the thing about this physical storm is that it was accompanied by a Twitter storm. 20 million tweets were sent about Hurricane Sandy. And the thing about Twitter, of course, as you all know, is it tells you what's happening, where it's happening, when it's happening, to whom it's happening, and so on. So you know exactly where you should send the emergency services. Except, consider this, imagine a village, a community, which has been completely obliterated by Hurricane Sandy. All the power's down, all the phone masts are down, and so on. You wouldn't get any tweets from that community. You wouldn't know that that's really where you needed to send the emergency services. So again, crucial absence of data, crucial missing data, crucial dark data. Okay, now let me take a step back. We all know about the power of data. The media are full of it nowadays. They tell us that data plus data science, statistics, algorithms, AI, machine learning, and so on, leads to improved understanding and better decisions. And that enables us to make better government policies, improve sporting performance, more effective medical treatments, better customer understanding, scientific breakthroughs, and so on and so on. And we're all familiar with these sorts of phrases. The media is riddled with these sorts of phrases: big data, machine learning, artificial intelligence, alternative data, and so on. But the thing about these phrases, which are all over the media at the moment, are that they tell you about the data you have. They don't tell you about the data you don't have. Think of my examples. They don't tell you about the problems that can arise, the misunderstandings, the wrong conclusions that can be drawn because you're missing some crucial data. In short, they don't say that the data you don't have, the dark data, can be even more important than the data you do have. Okay, sometimes people say to me, yeah, this is a problem with sort of small data sets, traditional. Not a problem when you've got billions of data points. That the sheer number of points swamps these problems. That, in fact, is not true. In fact, quite the opposite is the truth. Big data sets have data sets and extra problems of their own. Think about it, 1 billion data points. Well, there are 32 million seconds in a year. If you were to one at a time, which you can do with a small data set, but not with 1 billion data points, take you 30 years with 1 billion data points. So they have extra problems of their own, large data sets. Okay, so I'm going to give you a couple of examples, a couple more examples in more detail. One involving very small data set, one involving large data set. This one is the small data set, and you'll all recognize this. It's the space shuttle. And this is one of my favorite examples because it involves just 7 data points and 7 fatalities. So very serious problems with dark data. And what I'm going to be telling you about, and I think familiar with this at some level, I'm going to be talking about the Challenger space shuttle disaster, January 1986. The Challenger space shuttle, well, if you look at this picture, you can see the brown fuel tank in the middle and the 2 rocket boosters on either side of it. Those rocket boosters are made up of segments, and between the segments there are seals called O-rings. And it was well known that malleable, less flexible when the temperature is low. And what happened to the Challenger? 73 seconds after launch, 9 miles high, one of these O-rings developed a gap. A jet of flame projected through the gap onto the strut, supporting the booster rocket to the side of the fuel tank. The strut crumpled, the jet of flame projected onto the fuel tank, and 73 seconds, 9 miles high, the thing blew up. The astronaut compartment, crew compartment, went into a ballistic trajectory, continued up to 12 miles, and then crashed into the ocean, killing all the 7 astronauts. Now, it was known about the lack of malleability seals, and the night before the launch, the organizations responsible for building the thing had a teleconference, and included in the teleconference, they looked at this plot. Each dot here represents a previous shuttle launch. The horizontal axis shows air temperature on the day of the launch, and let me just do this. And the vertical axis shows number of problems on that launch. So at the lowest previous temperature, which was 53 degrees Fahrenheit, 3 of these O-ring seals had a problem. But on the other hand, at the highest previous launch, which was 75 degrees Fahrenheit, 2 of the O-rings had a problem. 2 of the seals had a problem. On the basis of this, the people at the teleconference looked at it and said, well, there's no very clear relationship between number of O-ring problems and air temperature, so we'll go ahead. At this point, if I was giving a lecture to my students, I would pause and say, there's something funny about this graph. There's nothing wrong with it, but it's a little odd and it might arouse suspicion. And I would pause there and ask you what you think it is. But I'm not going to do that because I haven't got time. I've got lots of other things I want to talk about. So I'm going to tell you what's odd about it. There are no launches where there are no problems with O-rings. There are no dots on this 0 problems with O-rings level. So it looks as if all launches have at least one problem. That's a bit odd, isn't it? It's not wrong, but it's a bit suspicious. In fact, the truth is that there were previous launches which had problems with the O-rings. And if you happen to know how many previous launches there were, you'd know that there's some missing data, some crucial dark data. I'll fill them in. That's where they are. Without those, it looks as if there's no clear relationship between number of O-ring problems in air temperature, but put those missing data in, those dark data, and there's a very clear relationship. At lower temperatures, you've got quite a high probability of a problem. At higher temperatures, well, only 3 out of all of these, only that proportion had problems. So it looks like the lower the temperature, the more likely you are to have O-ring problems. And if I now also fill in the forecast air temperature for the day of the launch, the next day, you will see that you probably would have decided not to go ahead with this launch if you had seen all of the data, including those red points. So crucial dark data missing from their deliberations, leading them to draw, I think it's fair to say, the wrong conclusion. Okay, let me move on to a large sample example. What I'm going to do is compare with that in the US. And here are the figures. For men, per 100,000 in the population, the death rate in Japan is about 41, and in America, it's more than twice that. Okay, fair enough. Now let's look at the risk factors for heart disease. Well, one of the primary risk factors is smoking. And in Japan, more than twice as many, at the time of this study anyway, more than twice as many men smoked as in the US. So that's a bit odd, isn't it? Because smoking's bad for heart attacks. You would think with that risk factor being twice as high in Japan, you would have probably more heart problems in Japan than in the US. Here's another risk. High is bad, and again, it's worse in Japan. And here's another one, cholesterol level. High is bad, worse in Japan. Now, this is odd, isn't it? Admittedly, these risk factors are probably correlated, but even so, with all of them sort of implying it's worse in Japan than in the US, it's curious that the death rate in Japan should be less than half of that in America. Now, of course, we all know, or the received wisdom for why this occurs is because the Japanese have a diet which is, and fish oil. Fish oil contains a substance called omega-3, which is protective against heart attacks. That's fair enough. But now consider this. Heart attacks are a low status disease in Japan. They imply manual labor, like digging roads and so on. In contrast, strokes are a high status disease in Japan, implying cerebral labor, thinking, sort of thing you guys would do. I'm going to suggest to you that perhaps it's possible as a heart attack in the US is differentially classified as a stroke in Japan. So we've got a problem with our data in that we're hiding things because of different definitions. I'm not saying one is right and one is wrong. I'm just saying things are being hidden. Of course, if this explanation is right, we would expect to see a higher rate of strokes in Japan than in the US, a sort of compensating thing. And in fact, you do. The stroke rate in Japan is 50% more than that in the US. Now, don't misunderstand me. I'm not saying that against heart disease. What I'm saying is perhaps both of these factors, the second one being dark data, contribute to this curious contradiction at the beginning. Okay, my book gives a taxonomy of 15 types of dark data and a couple of sort of introductory remarks. I don't think it's comprehensive. One of the reasons I don't think it's comprehensive is that new ways of collecting data are coming along all the time. In the last few decades, we've had sort of genomic data, proteomic data, social media data, all sorts of new things coming along in time. And I think new ways of collecting data lead to new kinds of dark data. But more important than that, the 15 types are not mutually exclusive. If you look at your study, your data set, and you identify that it's suffering from a particular kind of dark data, try to do something about it, that doesn't mean it's not also suffering from others. You can't relax. Different kinds occur together in a sort of diabolic synergy, if you like. They can make things worse. Okay, let me look briefly at some of these. 2 of these 15 types will be very familiar to you. Their data don't know are missing. And the reason they're familiar to you is they're Donald Rumsfeld's very famous known unknowns and unknown unknowns. So here's a little example of known unknowns. I've got a survey. This is from a survey in which age, height, weight, and sex were recorded. But you can see that the second row, the person represented in that second row, has an NA not available for age. Now, we know they've got an age, we just don't know what it is. So it's a known unknown. In contrast, people who don't respond to a question in a blog are unknown unknowns. We don't know who read the blog. We don't know who wanted to respond but didn't. We know nothing about them. They're unknown unknowns. My third type of dark data is choosing just some cases, sample selection. Psychics are great sort of exponents of this kind of dark data. They make many predictions and then just draw your attention to the ones they get right, ignoring all the others. So they're giving you a distorted impression of what's going on. They're concealing the bulk of their incorrect predictions as dark data. In fact, the organization Gartner has a definition of dark data, which isn't as broad as mine. They just define dark data as this type 3 dark data. They define it as the information assets organizations collect, process, and store, but generally fail to use for other purposes. So they've got the data, but they're not actually making use of it. They're ignoring it. My type 4 dark data is a variant of type 3, a special case of type 3, self-selection. And my little illustration is the customers who shop at a particular store. Suppose you run a store and you want to increase your customer base. Well, what you want to do is analyze how customers behave so that you can put things on the shelves that they want, that sort of thing. But of course, you've only got data about the people who shop at your particular store. So you could analyze the data on the people you've got. But by definition, the people you're trying to recruit are behaving differently. They decided not to shop at your particular store, for instance. So they're behaving differently. So you may be missing something crucial there. And it's self-selection because people themselves choose where to shop. Okay, so far, all of my examples have involved either particular characteristics like the age in that little survey missing, or they've involved complete records missing, like the unknown knowns. You know nothing about the people who don't reply. My fifth type is sort of orthogonal to that. I'm going to look at particular variables being missing, and I'm going to illustrate with the Titanic disaster. So here we've got a little table comparing crew and third-class passengers' survival rate. There were 908 crew on the Titanic, and 212 of those survived. 627 third-class passengers, and 151 of those survived. So here are the rates. You can see you're better off being a third-class passenger than a crew member. Not much better off, but nevertheless, third-class passengers have a higher survival rate than crew. That's clear enough. Now let's look at this, just look at the men. Here are the figures: 888 male crew, 192 survived, similar for third-class passengers. And here are the proportions. You're better off being a crew member if you're a man. And what about women? 23 of the crew were female, and so on. And here are the proportions. You're better off being a crew member if you're a female. Now, this is odd, isn't it? You're better off being a crew member if you're a man. You're better off being a crew member if you're a woman. But overall, you're better off being a third-class passenger. This looks very puzzling. It looks contradictory. And of course, when I present tables like this to you, when you see a contradiction like that, the first thought you should have is, I've made a mistake in the arithmetic. But you've got all the numbers there, so you can check. In fact, this is a well-known phenomenon. It's called Simpson's paradox, and it's to do with the way we calculate averages. I'm not going to explain it now. It is explained in the book. I'm not going to explain it now because what I want to do now is simply draw your attention to the following. Suppose I was interested in making more women, but I hadn't recorded whether they were male or female. I would have to make my statement just on the basis of these proportions, and I would be wrong. Missing dark data can lead me astray. So here are the other 10. I'm not going to go through them in the sort of detail I've been through the others, but here are the other 10 types of dark data in my taxonomy. Oh, I should say that my book was published in 2020, months before the pandemic, the COVID pandemic hit, which means that the word coronavirus, COVID, they don't appear in my book. It would be entirely possible to write an entirely book about dark data with COVID. But what I thought I'd do, I've I'm going to run through a few of these very briefly and illustrate some of the dark data problems which threw up during the course of the pandemic relating to COVID. I won't do it in great detail, but and they've now mostly been resolved as time has moved on and we've collected more data. But they're they will illustrate the problem. So data which might have been. When the initial clinical trials were run to test the vaccines, there was a particular gap between, but when they were rolled out in the UK, I don't know if this is true in Portugal and elsewhere as well, but in the UK, they extended that gap when the vaccinations were actually rolled out. But of course, there was a discussion, a controversy about whether that would mean that the vaccinations weren't as effective. There was missing data about what would happen if you delayed the second vaccination. Delaying it, of course, meant that they could vaccinate more people. So missing crucial vaccination, missing crucial information about delay in the vaccination. What about changes with time? Well, early on, as news of the virus appeared, there were discussions about how serious an impact they would have. We all know the results now, but at the time, there were questions about whether data on one variant would apply to another. What about definitions of data? This is a bit like my favorite of the examples, actually. On the 28th of May, 2020, the UK was reporting 206 COVID and 37,000 deaths. In contrast, Russia was reporting 50% more cases, but only a ninth as many deaths. So what's going on? Was it much safer to live in Russia, or what? Or were there different definitions? Were they talking about dying of COVID versus dying with COVID? Dying with COVID symptoms, or dying when you've had a formal test for the presence of the virus, and so on? Different definitions, different ways of describing things. Some things are being concealed inadvertently. What about summaries of data? We all know that summaries, by definition, don't give you all the details. If I tell you an average, you don't know if everybody's got exactly that value, or lots of people have a value smaller than that, and just a handful have a value much larger than that. You don't know. Summaries hide things. And the same applied with COVID. Different countries were proudly reporting their infection rate, their death rates. But of course, we know that those rates are not uniform across the country. It could be entirely possible that a particular country is reporting a low death rate, but you happen to live in a hotspot where it's quite serious. So summaries of data, again, can hide things. And then finally, on feedback and gaming, my 11th kind of dark data. As the vaccine was rolled out, we didn't know how people would behave, whether people would say, I'm vaccinated, I'm immune, I can go out, party, rave, or whatever people do. And it's entirely likely that their behavior would change. And that, of course, would feed back and have an impact on the infection rates and so on. So some examples of dark data from the pandemic. Incidentally, and I think this community will be particularly interested in this, the reproducibility crisis in science, certain sciences anyway, is largely due to particular types of dark data. So many of you will be familiar with the file drawer effect. You carry out a study, you collect the data, but it's not a very exciting result. It didn't sort of contravene some sort of theory or whatever. So you say, oh, well, I've got to write that up, and you put it on your desk. And then, of course, you've got to prepare next week's lectures or departmental papers or whatever. So you put it aside, and then results of another experiment come in, much more exciting, and you focus your attention on that. As a consequence of this so-called file drawer effect, the reported studies which go into the literature are distorted, and those studies which don't get written up go into a file drawer as dark data. Regression to the mean, similar sort of distortion. Large effects will be due to a real underlying large effect and chance. If you repeat that, you're likely to get the chance being a low value or a lower value. so that you will find that the phenomenon, the effect size, the reported observed effect size isn't as large. Observationally, you cannot separate the true effect from the chance part. So and p-value hacking is another example. It doesn't just refer to p-values, where people trawl through data and pull out the ones which are exciting, important, significant, or whatever, focus on those, don't bother to report the others. Incidentally, all of these phenomena do occur, and one surprising consequence is that the more prestigious the journal, and this is true, the more likely it is to contain results which are later retracted. It's not just me saying this, there have been studies which actually look at this. Okay, so I'm sort of a bit over halfway through, and my real aim in this talk is to alarm you, to make you think, oh my God, this is dangerous. We have a problem here, so that you rush out and buy the book and see what you can do about it. But what I want to do in the remainder of the talk is look at two things. One, how we handle this sort of problem, and two, actually, we can take advantage of it. So how do we detect dark data? Well, I'll very quickly go over some examples. Very occasionally, it's obvious. First, this is also one of my favorite examples. The Actuary magazine on this date included an editorial which said, a couple of months ago, I invited all 16,000 of you to participate in our online survey. And then it went on to say, I'm pleased to say that a number of you, 13, not 13,000, just 13, replied to our poll. Practically all of the data are dark here. I'm pleased to tell you that the editor of this journal didn't then say, oh, well, I'm going to analyze these 13 anyway and report the result. That's not quite true. He did analyze it to the extent that he said, I've concluded that actuaries don't reply to online surveys. Okay, the basic strategy for detecting on dark data is to compare what you've got with what you'd expect. I'm not going to go through these examples in detail, just very quickly. We can talk about them afterwards, or you can email me if you want more details. This is what's called a funnel plot. It's for analyzing clinical trials, whether there are missing data, and it ought to be symmetric. But there's a sort of dearth of data points in the bottom left. That suggests that there's something missing. Here's another little example. This is ambulance response times, and it shows a huge apparent spike. Lots of ambulances turning up exactly on 8 minutes, which, funnily enough, was the target time. Clearly, there's something funny there. Clearly, there's distortion going on. And my final little example with one of the biggest investment banks on anti-money laundering. This is, some of you will recognize. The black bar chart shows you the expected distribution. The orange bar chart shows you the empirical observed distribution for transactions. Actually, it's first digits of transactions. And they're different. That doesn't mean that there is money laundering going on, but what it means is there's something funny going on. At least we need to explain this. So a basic strategy is to compare with what you'd expect. But then what do we do about dark data? Well, you can use complete case analysis. Here's my little survey again. Complete case analysis. Only use those records for which every value has been recorded. Trouble is, of course, if you've got a lot of missing data, you might not have very many rows recorded, complete cases recorded. And if you look carefully at this little example, you'll see that the sample size has been reduced to 0. There are no rows which don't have at least one missing value. So you might dramatically reduce your sample sizes if you use complete case analysis. Another simple alternative is to use all available data for each variable. So I can calculate age on the 7 values which are recorded. I can calculate height using recorded. Trouble is, and that will be obvious, that the estimates will be based on different samples. In fact, if you calculate correlations, this can lead you to contradictions. These simple approaches which perhaps proudly proclaim they can handle missing data. And this is the sort of way they do it. And, well, you can clearly get misleading results. Okay, then we get more sophisticated methods. I could, with the age example on the previous slide, I could impute the average of the observed values. Perhaps not a great idea because, you know, let's face it, it's likely that the missing values weren't all identical for a start. So you're reducing your variance doing this. I could do something like that, but in a more sophisticated way. From pairs of variables which do have common values, I can build a regression model and try to predict the missing values. And which seek to do this in various highly sophisticated ways. I'm not going to go into those in detail, but I want to caution you at this point, which is that statisticians and data scientists, you guys, can use powerful machine learning, statistics, AI tools to do amazing things, but they can't perform miracles. It's much better to recognize, avoid, sidestep dark data and try to cope with it after the fact. Okay, so here's my basic principle for tackling dark data. You shine a light, you use what you do know about what you don't know. And I'm going to give you a little example. What I'm going to try to do is estimate what would be the average final score for a school student in that school had been examined. The data I've got are the final exam score for those who did sit the exam, some didn't, and we'll see those in detail in a moment. And I've also got previous test results for everybody over the last few years. The exam scores for those who didn't sit the exam are the dark data in this example. Okay, I'm now going to describe 3 statistical mechanisms for dark data. This is based on Donald Rubin's taxonomy, but I've changed the name because I think his names are pretty opaque. My first NDD, it stands for not data dependent, when something is missing for reasons unrelated to the data. So here we are in my example. Sickness might prevent students from sitting the exam, and sickness will impact the able students, the less able students, and so on at random. So it's not related to the data you've got, the data you haven't got, or anything. My second is seen data dependent, where it's missing for reasons related to the data you have got. And in my example, a school might discourage the less able students, and it knows they're less able because it's got the test results. It might discourage them from sitting the exam. And then finally, unseen data dependent, where it's missing because of the values you would have obtained. So, for example, a student might realize they'd revised the wrong material the night before the exam, so they didn't turn up to sit the exam. Not data dependent, seen data dependent, unseen data dependent. So here's my example. Horizontal axis, previous test results, vertical axis, exam result. Plot, and they're correlated. And if I had all the data like this, I could easily calculate the average exam result. But I don't. Let's look at the NDD first. So that's the complete where the data are missing in a way not dependent upon the data you've got. So it's just a random sample. I can still calculate the exam result. It's just that the variance would have been increased. But that's not a problem. It's unbiased. So here's my complete data again. Now what I'm going to look at is seen data dependent, where the fact that data are dependent depends on information you do know. And if I toggle between those, you can see that any student with the previous test result is more likely to not be allowed to sit the exam, not turn up. So it's seen data dependent. If I calculate the average of the exam results just using this raw data, it'll be biased upwards. You can see that from the graph. But if I condition on previous test results, if I just look in that little rectangle, there's no bias going on in that little rectangle. It's not a very big sample, admittedly, but there's no bias going on. I can estimate the proportion, I can estimate the average exam result in that little rectangle. And I can do that for every regression line, and then I can use that to adjust my estimated average exam result. Back and on to the third kind, the unseen data dependent. This is where whether something is missing depends upon the value which would have been recorded. And you remember, student realized they'd revised the exam, realized they'd revised the wrong material, so they didn't turn up to sit the exam. So you can see that those students who would have performed poorly are preferential. Now, if I calculate the average, it will be biased upwards again. And worse, if I calculate the average in that little rectangle, it also is going to be biased upwards. I can't fit the simple regression line. So I have to look at this particular case in much more detail, much more carefully. The book goes on about this in more detail and suggests ways around these problems. Okay, let me begin to wind up. I talked about the dangers of dark data. I've very briefly talked about how to spot it and what you can try to do about it. I'm now going to change tack altogether and talk about how you can take advantage of it. I call it the strategic application of ignorance. It's revealing by concealing. One of my favorite little examples is a very old one. In 1927, Holland adopted a confidential system of death. And the number of deaths attributed in Amsterdam attributed to syphilis increased dramatically because people aren't saying that it's confidential, identities aren't being given. So what's happening here is that previously invisible data, deaths due to syphilis, is being made visible. And we're achieving that by making identities, other data, invisible. We're revealing by concealing. And of course, you do this all the time, this sort of thing. You might want to keep your medical or financial records dark, so you use passwords, which keep data dark. And of course, they themselves need to be kept dark. So you're taking advantage of dark data. And a couple more slides. The dark data perspective can be used to look at all sorts of familiar statistical and machine learning tools. Sample surveys, for example, the normal way of describing sample surveys is that you sample 10% of the population. But of course, that is that you make 90% dark. Randomized controlled trials, of course, are randomized. You hide which treatment is given, blinding, very literal sort of darkness. So standard methods can be looked at. You can flip them on the head and look at them from a different perspective, the dark data perspective. And many advanced statistical methods use dark data in the form of data which could have arisen. You didn't observe it, but you could have observed it. So, for example, one of the familiar tools, which many, perhaps most of you will use, will be to generate multiple data sets using whatever your theoretical proposed model is and look at the results. This is called simulation. Another is to generate extra randomly perturbed copies of the data and then analyze all of the data set, including these copies. That's called regularization, or smoothing. Another strategy is to take multiple subsamples of the data, fit models to each of those, and look to see how different the estimated parameters are. That, of course, is the bootstrap method. Another is to generate, in classification problems, generate copies of cases, points that it got wrong, your model got wrong, add those misclassified points to the data set to lead to an enhanced data set which places more emphasis on the ones it struggles with. This is called boosting. And of course, finally, one can use additional imprecisely specified data, dark data you haven't actually observed. You don't know what the actual numbers are, but you know what the distributions might be. And that's, of course, Bayesian methods. All of these tools, or these classes of tools, use data you didn't see, but you could have seen, leading to these very powerful classes and methods. So let me wind up. Towards the last half of this talk, I talked about sophisticated use of dark data and demonstrated that it can be a very powerful sort of way of thinking about things, very powerful tool. But the first half of the talk, and in some sense the important bit, is to note that dark data, with a little anecdote, the elephant powder man example, I'm going to conclude with a little anecdote. This is as well, the drunk looking for a wallet beneath a lamppost. You come across this guy and he's leaning against a lamppost, peering down at in the spot of light cast by the lamp. And you say, have you lost something? And he says, yes, I've lost my wallet. And you say, where did you lose it? And he said, he points over there into the darkness and says, I lost it over there, but I can't see over there. And what I'm suggesting is that if you ignore dark data, you're behaving like that drunk. Here we are, my conclusion. Thank you very much indeed.
Thank you very much, David. It was the most fascinating and enlightening talk.
Yes.
So we are now ready for some questions. Who wants to start?
Yep, very happy to.